start? Okay, I think we are recording. Good. So welcome all to this second episode of our podcast or vodcast on wireless power transfer initiative. Today we have with us Jasmin Grosinger. She's an associate professor at the Institute of Microwave and Photonics Engineering at Graz University in Austria, where research focuses on sustainable wireless electronics and systems. She also holds a position as a visiting associate professor at the Graduate School of Engineering at Tohoku University in Japan. She's a senior member of IEEE. She has co-authored numerous peer-reviewed publications, book chapters, and invention disclosures. And for her PhD work, she received the first prize from the Industrial Union of the Austrian Automotive Industry Jubilee Foundation. In 2021, she was honored with the Mind the Gap Diversity Award from Graz Universities of Technology. And from 2019 to 2024, she served as associate editor for the IEEE Microwave and Technology Letters, and is currently the inaugural editor-in-chief of the IEEE Journal on Wireless Power Technologies, which, by the way, will be out in 2026, which is very good announcement for all wireless power technology community. Well, Jasmin is also an active member of the IEEE Microwave Theory and Technology Society, where she contributes to the technical committees 25, Wireless Power Transfer and Energy Conversion, and 26, RFID, Wireless Sensors and Internet of Things. Recognized as a distinguished lecturer by the MTTS, she is also an elected voting member of its ATCOM committee and chairs the meeting and symposium committee since 2024. So welcome, Jasmin, to this podcast.
Thank you so much, Nuno. I'm happy to be here and a bit nervous, I have to say.
No, this is a very relaxed moment. Sorry. As you know, we have a strong community on wireless power transfer. And the idea of this podcast is that we actually go through the technology and share with our colleagues and enthusiasts what we do. And for that reason, I will start with the first question for you, which is, why did you start working on this field?
Yes, so why did I start working on wireless power? So I did my PhD already on one technology that you know very well, RFID, radio frequency identification. And I started to work like at the higher ISM bands, the standardized RFID, UHF RFID technology, so at about 820 megahertz. And there you always need, wireless power transfer to communicate with the battery-less device. This is when I started, but we've never called it wireless power. We just called it, powering up the chip, the battery-less chip, so that we can communicate with it. And so when then I started my postdoc phase and I moved to Graz, I was starting to collaborate with NXP Semiconductors. And they were interested in HF RFID, so high frequency RFID, so at 13.56 megahertz. And it's close derivative near field communication, NFC, that we're going to talk about in this podcast. And this is when I started to work really at 13.56 megahertz and at magnetic resonant coupled systems, also using power transfer, but still communication on top of it. So to power up, your smart card that you use for payment. And NXP was actually interested in, so how would NFC interfere with mobile charging interfaces that you also have on your phone? And I can just show you an example that I have with me. Just let me share it with you. So I hope you can see it now. So
yep.
It actually looks like this. So the idea for, or the question, the research question that NXP provided to me is, so how is NFC, near field communication, as you can see it here, this is an NFC coil in a mobile phone. It's actually a Huawei phone that was dismantled, and a student sent me the pictures. And there you can see the NFC coil that you use for contactless payment on the phone. And next to it, you can see here now the wireless charging coil operating at 100 kilohertz following the key standard. And the question, the research question they asked were actually, so how would this key wireless power transfer system interfere with NFC? In the case of the mobile phone, would there be some extra capacitive coupling that we would need to take into account if these coils are next to each other? These kind of things. And that is the phone. But in the end, you also have these systems, even, in appliances in the kitchen. And you might have then, a credit card next to you. And what happens then with this smart card, this credit card, if you get it next to a key system that is a key wireless power transfer system that is very powerful? So these were the questions. And that is why I started to work on wireless power too. And of course, because of the initiative that is driven by IEEE and by you and your colleagues, the IEEE initiative on wireless power technologies, that is what got me really into wireless power. And I'm happy about it. It's an exciting field.
Yeah, good. That's nice. And before actually going through the NFC, what is, from your point of view, the difference between NFC and RFID? I know this question was not here, but if you can say 2 or 3 words so that people understand what is near field communications.
So the biggest thing about near field communication to HF or RFID is that you can emulate a tag, a smart card. So the phone can be both. It can be the reader and the transponder. And so this is what is the biggest difference. And NFC was invented here in the Graz region by NXP and the colleagues there. And this is what we're super proud about, of course.
Yes, I imagine. So you also show 2 coils, so one for wireless power and the other one, as far as understood, for the NFC on that phone. And when you have metal around your coils, what is the impact of that environment when you have to actually share NFC with metal? Is this a challenge? I know that you have been working on that.
That is definitely a challenge. And on the picture of the phone, we actually saw this black thing in the back of the coils below the substrate. And this was actually ferrite material, one thing that you can use to mitigate effect caused by the metal. But let me just, explain to you quickly how near field communication works. So NFC, as I said, it's relying on magnetic resonant coupling. So you would have your reader device, and you would have then on the right side here your transponder device, the smart card. And this is a magnetic resonator at 13.56 megahertz, and the other one too. And here on this side. And if you bring them together, they're able to communicate with each other or transfer power. So just as a side note, if you use it as NFC charging system, then you would not call the reader, but you would call it polar. And you would not call the tag smart card, but you would call it listener. So this would be then charging. But in the end, if you have metal next to it, for example, to the listener, then you would see that the magnetic field that is generated by this magnetic resonator at 13.56 megahertz is actually generating eddy currents in the metal next to it. And this is creating an opposing magnetic field that will then shift your inductance and will shift with your inductance, as you can see here, also your resonance frequency. So the coil inductance, as you can see it here modeled by this inductance, is then affected and shifts your resonant frequency. And so you wouldn't be able to operate then at the frequency you're attending to, and you would just not be able to operate at all, or would have just a very reduced read range or a power range, communication range.
So what is your strategy to actually compensate it? What is your ideas?
It's actually not only my strategy, it's actually a strategy by a lot of researchers. So it started back in 2006, and I published an article in the IEEE Microwave magazine where you can read through the history of what has been done to operate near-field communication devices robustly in metal environments. And just as a side note, you could also then maybe use these strategies for other wireless power transfer systems that rely on magnetic resonant coupling. You just would need another ferrite material, because there are more types of ferrite materials, and you would have to choose then according to the frequency you are resonating or operating. But what has been done is, for example, ferrite, and I can just share with you once again this slide that I showed you before so that you can see it more clearly. Wait a minute. There we go. So it would be ferrite material, as you can see it here in the back. This black flexible sheet is ferrite material, and it's one of the most powerful things to decouple the effects of metal on your system, on your NFC system. And you can see here the back side of it. So because in the mobile phone, if you think of it, you have the battery pack, and that is in just like enclosed by a metal housing. And so you would then need to operate this NFC and key coil next to it, and you would have a reduced read range for NFC, for example. And so you can use then the ferrite sheet, and it helps you really to get rid of the influence of the metal. And it has not that many losses. And sometimes and it will help you then to have a read range as you used to have it, or power transfer as you used to have it. This is one option, ferrite. Another option would be use ferrite, or what has been shown, we have shown it, but other researchers too, would be using ferrite together with booster antennas. This is something that would even allow you to communicate with a device that is enclosed by metal completely. So it's I could show you more details on this, but that's something that you could use. Or another thing that you can use is adaptive matching networks. So
when you said directive antennas is something that you put in front of your inductor, right?
Did I say directive antennas?
Or you did not say directive antennas? So I missed
like it's late in the evening for me. I'm not sure what I've said, really.
No problem. So probably I miss it. So because this was one of the questions that I have since
booster antennas.
Booster antennas.
Yes, I can show you a slide on this.
Yes, exactly. Because I was looking to these traditional phones. You can see it in my hand. You see now this cover that they have this booster. I think this is like a booster, MagSafe, right? So this is something that you are also considering for this activity. Let's say
I'm not that familiar with MagSafe. I have to say, I believe MagSafe is more like, I don't know it by heart, but for me it was more like, to align it perfectly.
Okay.
The two coils. And so that, because every misalignment would reduce the power transfer efficiency. And this is something that you would try to get rid of. And I believe MagSafe is just helping you to lock it in.
To align them. Yes.
This is what I think. Yeah. But I don't have an iPhone. I have to admit it.
No, this is not an iPhone, but now everybody's using this one.
It's really? Oh my gosh, I'm not using it. Like I have to.
Yeah.
No,
Yeah, please continue.
Now, for the booster antennas, this is something that is at the beginning very kind of not easy to understand. It's just because it's a very difficult arrangement. So here, for example, you have a setup that we presented as a so-called HF RFID repeater to extend the read range, or actually to allow communication between a sensor tag, or a listener device and a polar device, a reader antenna, a reader coil.
Yeah.
And you have then here magnetic resonant coupling and here magnetic resonant coupling. And in between, you just have metal. And we just had this scenario because we were collaborating with AVL List, and they are based here, the headquarters in Graz, and they're in the automotive supplier industry. And so they have a lot of metal and would like to read out, in this case, a sensor tag. So we provide power to the sensor tag that is batteryless in their measurement device that is in-house by Metal Closing. And we provide power from the outside just with a mobile phone acting as the reader or the polar. And to make it happen so that we can communicate through the ferrite, we use a so-called booster antenna, actually 2 booster antennas. Here you can see this is a so-called pickup coil that would be then aligned with your mobile phone. Then you have a small coupling coil that is aligned to a small opening in the metal that you would need. And on the other side, you have the same thing. And to get rid of this metal effect here, we used ferrite. So to decouple the pickup coil and the coupling coil, we used ferrite, and we used the ferrite core actually here in between. And then the opening, we also we put some ferrite on you call it maybe mantle, I'm not sure about the English word. And so we try to make sure that the metal is just covered by ferrite enough so that we are able to get the magnetic field through. And I can show you a video about it. I actually have it here. Where you can see one of my PhD students actually demonstrating it, but I just have to start it again and share it with you. Hopefully you can see it well done. So this is this sensor tag, and you can see it's during COVID times. And this sensor tag is just, an HF a near field communication tag, where we have an NXP Tamper tag that gives you a binary sensor interface. And so we actually added a read switch, and this allows us then to monitor if a temperature threshold is violated or not. And here you can see then the device. This is a sensor developed by AVL, of course, automotive industry, and they're testing and sensing engines. So it's a huge sensor, and here's the metal housing. And you can see then Richard, you were actually his PhD examiner. Thank you for that, Nuno. You can see him, how he's working on it. Like he's aligning now the sensor that is just also on metal with the one part of the booster antenna that is inside the enclosed housing. It's for hydrogen monitoring, I believe, automotive industry. That's crazy. And then you have the other part of the booster antenna here. And then you can see here the app that we use to read out. And you just then read out with the phone from the outside, what is the tag tamper status? And if here in this case, it's closed. But here you can see then, okay, we can read out, we can extend the read range and beyond metal. And in the end, that was a great achievement. And it's metal environment you will see in a lot of applications.
Oh, this is nice. So what you're saying is that you have the booster antenna, now I'm using the correct name, to actually, you also call it a repeater. So you can connect 2 different end devices with this repeater in the middle and go through a metal wall. This is what you're saying, correct?
Yeah. Yes. And the crazy thing actually is in the paper that we submitted to a IEEE antennas and wireless propagation letters, actually. There we're showing that with the repeater structure, yet not in this case in the video, but with a normal setup where you have a reader and a tag and just a measurement tower, there we actually showed that we improved the read range compared to free space. That's
Oh,
crazy.
so that this repeater, I saw that you have also some kind of resonance, so it's resonant
Yes,
to your frequency. What is the
13.56 megahertz.
30.56 megahertz? Oh, nice. And actually, you can use this in automotive, but other applications, do you foresee other applications where you can use this
For this
technology?
one, oh, yeah. So one of the reviewers, he was very, he was giving interesting ideas, in particular to respond to the other reviewer who was not happy with the paper. And the first reviewer actually suggested that would be a perfect thing, the setup, this NFC setup, for military applications where you have something in a case that shouldn't be opened, or you should know when it has been broken, the seal, so that you could
Mhm.
detect it.
Mm.
And this, with NFC, the distance is small, you have a lot of power, so at the sensor inside of this suitcase, you could have a strong security then, no? So this is one idea that one reviewer said, and so we responded it to the other reviewer because, like, I'm based in Austria. I'm not aware of any military applications. No.
So and what you showed in this video is that this was mainly for NFC or also to transmit wireless power.
It's always both, but
Okay.
for really NFC charging, so this
Yeah.
new standard that is coming
Yes.
up, I can explain. I can just show you quickly one slide, so that you have an idea about this standard. This was actually initiated, as you can see it here, by a forum, like the NFC forum. So it's a bunch of companies that are coming together and are promoting their standards. And they're promoting this standard, NFC wireless charging, as an add-on to key wireless charging, which is promoted and provided by the Wireless Power Consortium, as you can see it here. And
Mhm.
key is 100 kilohertz, about 5 to 15 watt of power, and designed for mobile charging. So we use it at our phone. And it's definitely, in this case, also more efficient, with especially at the lower frequencies,
Oh.
that the rectifiers are more efficient there.
Mhm.
And NFC wireless charging was now introduced as, of course, also having some communication on top, but for transfer of power where you just need a power up to 1 watt. So personal or wearable devices, they say you can power up, for example, then with your phone, you can power up then the watch. And they plan to future extend it to 3 watt. Of course, here the rectifiers are not as efficient as for key at the lower frequency, but still, in particular with these miniaturized coils that we'll see more and more coming, thinking of, your wristwatch or so, they're it's bringing benefits, and so they're promoting it, this NFC charging. And I have to say, it's something that we're working on. For example, I work with this company Renesas, former known as Pantronics. They do a lot of NFC wireless charging ICs. I'm working with them, with some students, to get a hang on it. So it's something that is new. It's already promoted by the NFC forum. There are already products there, but it's still, a matter how to improve the efficiency more.
Yes, exactly. Always improve efficiency, especially on wireless power. But so you already said one of the applications this can be used, for instance, to charge your watch, your smartwatch with your phone. Do you foresee other applications and other consumer electronics that will appear?
Yes. So you could have possibly, like if you think of you have your iPad or your phone somewhere lying there, and you just run out of power with your headphones, your earplugs. You could just position, your earplugs. You can just put them on the phone, and it's gonna be charged. Of course, it's not so efficient charging, but also not key is as efficient. I have a key charger on my desk, and I charge my phone with it, and usually everything is getting very hot.
Yes.
So it is what it is right now. But in the end, the pitch that I've heard once was very Austrian. It was again provided by Renaissance, by this company here in Graz. They said, oh, imagine you are hiking somewhere in the Austrian Alps and you run out of power on your smartwatch, but you want to track your GPS track and you want to track your vitals. And if you are someone into fitness, if you lose a bit of your session, you're devastated. And so he said, imagine, you just use then your phone, you have enough power there, and then just, charge it up, your wristwatch and your fitness watch, and then you see your GPS track. And to be honest, it's really a problem. GPS is consuming a lot of power. So if you have a long hike, your watch runs out of power like this.
Sure. For sure. So, and the frequency they will use for the charging is the same as they use for the communication?
Yes.
And the coexistence of both, how do you see that? What are the problems of coexisting NFC communications and NFC charging? It's same thing or?
No, the chips are a bit different because like the load is different and how the resonance is created, the arrangement of series, these kind of things. These kind of things are different. And so it's not the same, but still they have communication on top. So this is an add-on. And it is secure communication because the encryption is very strong. So
yeah, but a curiosity that I have, the communication will go on top of the wireless powered signal. So it's like swiped, so simultaneously wireless and information power, or it's a different thing. You have a part for wireless and what part for communication.
To be honest, I don't know it by heart. But I invited again for our next wireless power transfer bootcamp. I invited 2 people from industry talking exactly about NFC charging, hopefully. One guy from Renaissance and another guy from New Current. And they are very good in this. And maybe they can give us details how they do it, because I don't know it by heart. I can imagine right now, because the power transfer is just up to 1 watt, you can still handle it, communication on top. But for higher power, I'm not sure anymore.
Exactly. and yeah, I see. I also read about the possibility to have these lockers in your house that are powered by NFC charging, right? So you use your phone to somehow energize your locker, something like that.
You always, and that is the cool thing about NFC or HF RFID. You always have the power transfer part with it.
Yes.
So on the transponder side, the device side, the listener side, you can always be without, even without a battery.
Yeah, so this is something that it's going to a very interesting direction, this talk. So you see RFID and wireless power, they are actually connected, right? So you cannot break it somehow.
Not really. So, like a few years ago, SWIFT was coming up, simultaneous wireless information and power transfer. And I was always like, hey, come on, RFID is the same thing. But, like, I understand that it's maybe not the same thing because like RFID is doing, is piggybacking on the way back, like, and then for SWIFT, I believe it's more like on the how you would call it, on the uplink, no?
Uplink, okay.
Yeah.
Yeah, it's a
Or
full
isn't it like
communication
this?
thing. Yes, more or less. You can build it like that. Yeah. So another question I have here for you is how do the sustainability factor will impact the future at FC and WPT? Do you have a comment on that?
Yeah. This definitely. And this is because we use ferrite a lot to decouple from the metal environment, but ferrite is a rare material. So some companies already say, we do not want you to use ferrite, decouple from the metal environment, and you usually have a metal environment next to it. So you have to think of alternatives, and we've started to work on this and submitted it to the WPTC conference, actually. You can see it here, it's metasurfaces. We're working on it. I'm working on it with a postdoc, Zara. She's a metasurface person, so it's a good combination. And you would see here a class 1 size coil. Class 1 size means in NFC that it's 8 times 4 centimeter, as big as your credit card, and you would have a 20 picofarad chip to create the resonance at 13.56 megahertz. And then in the back, you would have then this metasurface. And you can see it's actually, there are huge resonators there, and we need capacitances to make it happen. But if you take a look here at the magnetic field versus height, you can see that we have actually in one case a very high magnetic field with the metasurface, and it's way stronger than a standalone again. So it gives you a big boost, and it's a bit more sustainable. What I'm not happy about is that we need capacitances because this is additional component, so it's not so sustainable. But we're just starting on it, and there will be a special session that is organized by some colleagues, and they also asked us to submit there. And there are also some other papers coming into this special session. And I reviewed one and suggested to accept it because it's really cool by some Italian colleagues. And I hope really that we can get together, get more ideas. I'm also not happy about that you need a certain distance. So a certain distance between the metasurface and the coil, that's not cool, because this is then not comparable to have a coil printed on ferrite and a very thin creation that you can easily embed in your phone. So I'm not happy with these things and how bulky it is and the substrate. So we still have to tweak it. But the first thing we have to do is really showing measurements that they are comparable to the simulations, verify, and then move on and see how we can make it a bit more integratable in a phone, for example, because otherwise then industry is not interested. No,
No,
if it's
for
very
sure.
bulky. Yeah.
So your idea is really to substitute the ferrite with the metamaterial. And your preliminary studies show you lose efficiency, or
no, we gain.
You gain efficiency.
Even in comparison to really the standalone.
Mm-hmm.
Well, in comparison to the ferrite material.
The ferrite material, yes.
Incredibly.
Even if on the other side you have metal, right? So you have
Yeah.
metal, you have the metamaterial, and then you have your inductor. Oh,
Yeah.
nice.
But it's just not thin enough yet. It's too bulky.
Okay. Yeah, exactly. Yeah.
So
And you need a capacitor, you said. So you
yes, an additional component.
Yes,
But
exactly.
let's see. I saw these papers. So this one paper was quite interesting in terms of being, having a thinner realization. So I like this a lot. I'm super excited to speak with the people there, learn more. So metasurface is not my field, but Sarah is working on it, and it's quite promising to see. Yeah.
And the first, please.
No, you go ahead.
No,
because
I was
otherwise
saying that in the first talk we have here, Manos talk a lot about different materials that you can use. Do you think you can also bring new materials to your structure, to the metamaterial area?
I have no idea. So as I said, I'm just starting to learn about meta surfaces, but I could imagine to have something like this. But what I would not like is to use another rare material, because then it's not
Mhm.
sustainable anymore.
Yes,
Yeah,
I understand it.
yeah.
Mm. And for you, what are the biggest hurdles that you think we will face before a wider adoption of NFC wireless power? And a challenge question I will put you now is, do you think NFC charging will remove the Qi charging from mobile phones,
Don't
or they
think
will
so.
continue to coexist?
Coexist. Like usually it's a coexistence of different technologies. Like standardized RFID and chipless RFID. The two of them are battling each other all the time at the conferences. You meet the people doing this and this, and they're picking on the other's technology, but in the end, it's always a coexistence. But the efficiency improvement also for key. Like
Mhm.
it's still getting so hot. That's not cool. Who would like to have this in terms of in times where we want to be sustainable? Who want to lose power?
Yeah.
So this is what we have really to work on. Another thing that might be an idea to use, as I said, no, you would need to align the coils quite tightly and nicely, so that there is no angular misalignment, or there is
Yeah.
no lateral or misalignment or so. Because if you have this, you have a reduction in power transfer, no? In a power transfer efficiency. And so what you could do is you could use adaptive matching networks. And we actually did this. We showed this. And let me share my screen with you. I have another video. It's not edited, but you will get the idea. So you could see here, is it? It's not. Isn't the video working? Oh yeah, there we go. So you can see here 2 class 1 size coils, so dedicated for wireless power, with the arrangement of the capacitance, so that we have a series, I believe, so that it's working nicely. And we have a little measurement setup so that we can change the distance between the polar and the listener coil. And we created here a bit of an adaptive matching network that we can steer then. So if we have a misalignment in laterally or angle in angle, so that we can adjust then at the polar side the matching network, so that the power transfer would be better again because of this misalignment due to
Mhm.
changing. And one thing is, you can see we have here, so this matching network where we have a varactors in there that will steer then with this voltage supply, and everything is actually adaptively real-time matched using a little surrogate model that we trained. So a little machine learning algorithm that we trained based on our simulations. What kind of, you just simulate what are the scattering parameters, and then at the polar side, what is then the input impedance that you see, and what would then match then again to the 50 ohm that you want to match to. And we actually could show, yes, okay, we have an improvement in power transfer. But in the end, the matching network, as we have it like here with these varactors, is draining a lot of power. So
Yeah.
this is really not cool. So, and we saw this affects quite considerably the power transfer efficiency, in particular if you use FO4 coils, NFC, class 1 size, and really FO4, because there the efficiency is not super high, no?
Mhm.
This is just cheap for consumer products, no? And so the efficiency is already low because of the setup as it is. And then with the losses in the matching network, it's getting even, like worse.
Yes,
But we do see, we improve let's say it like this. I might say it wrong before. We improve the matching, but we don't improve the efficiency.
yes.
Let's say
Yeah,
it like this.
I understand.
But the idea is we just wanted to play around. Okay, how can we use machine learning? Can we use then the MATLAB toolbox? Is this suitable for us? And we demonstrated it, but the idea would be to have this matching network integrated in CMOS. And then use a tiny AI algorithm that we trained, or any kind of other real-time algorithm that helps you to steer. That is actually, right now you have these little HF RFID chips with capacitor banks, where they switch just automatically without any intelligence. And if you have this integrated, you have less losses. And then you have a better performance.
Yeah, it's good that you brought the machine learning AI, because I was I will ask you about that. First of all, I really like your setup, the measurement setup. It's very clean
Nuno,
and very beautiful.
Yes, I have to add here, this setup was done by Jose, and he did his PhD thesis on power amplifiers. So
Yes,
I reckon
good.
that you like it.
It's very clean, very beautiful. So, but when you bring AI to this setup, the AI core will not, let's say, consume energy.
Yes, it will. That is
Yeah.
why it's so necessary to work with the computer scientists.
Yes,
So
exactly.
really on tiny AI stuff, you know, like, because this massive AI where you have these machines where you run the data, and you know, like these large language models, you know, like ChatGPT, they are just, you know, using a lot of power. But the tiny AI stuff, they're already down to operate the devices at milliwatt levels.
Okay.
So
Yeah,
I'm
because I
waiting for
remember
further improvement to
exactly. I
microwatts.
remember you create a panel session 2 years or 3 years ago on tiny AI. Yeah, exactly. So you think you can go down to microwatts?
Yeah, I hope so. Hey, the fogs, you know, they are working on it, getting rid of the layers, and they call it pruning. I have no idea, you know, I just repeat what I've heard by then. So I'll trust these people, the computer scientists, to come up with good ideas, and I just then use it.
Yes, exactly. So the other question I have here is, do you think we will integrate NFC more and more with IoT, smart environments? How this can be done in the future?
So NFC in smart environments, that you can do, but you always have to think of, okay, because like you have with NFC the communication, so you can read out sensor data. But of course, you always have to think of the communication range is a short one, because you're based on magnetic resonant coupling. And, you know, the smaller the resonator, it's not getting better if you miniaturize the stuff. But I have a video for you where you can actually see how this NFC is already used in such a smart IoT application. It's done by, wait, I'll share it with you. It was done by Walter, the first PhD student I worked with as a postdoc. You can see it here. We might have to start it from the beginning. Let me see if I can do this. There we go. So you would see then the small tag is with a small coil, so 13.56 megahertz resonant, more or not, you know, like then a tissue bag. So the Walter wanted to embed the tag, the NFC tag in the body. And then you would use again a booster antenna as a blaster. And that's helpful. You just have to align then the little coupling structure with the coil on the chip. It's 1 square millimeter in size, the coil on chip. And then you read out the sensor data. And you can see it's back in 2013, Walter was showing this. The read range is super small, because like the power transfer is also very small, because we use this tiny 1 square millimeter on chip coil. But that's an application you could use too. And Walter was always thinking about this application a lot. He was even suggesting to tag Nespresso capsules with a capacitive coupled tag, all these kind of things. And he put in patents one after another.
Oh, nice. And what is, if you have an idea, the cost of it? Do you think it will be so low cost that you can, like RFID, you can put it everywhere, or do you think we still have to reduce the cost even more
For
for the
these devices
NFIC
as
check?
sensors,
Yeah.
no, this is so the thing is, you bring down the costs, the more chips you produce, no? The more
Yes, for
chips you
sure.
have on wafer.
Oh, okay.
Yeah. So so you need these applications where you need a lot of chips, and the consumer market is provides plenty of opportunities. So for IoT, there are plenty of opportunities to bring down the costs.
Bring
And
down.
even the designers, the engineers, they are working on, making these devices even smaller. So going to smaller technology nodes from 130 nanometer down to 40 nanometer CMOS. So the device, they get smaller and smaller. Of course, the RF behavior is getting worse and worse, and we really have to struggle to get have a nice RF DC converter on chip. But it's so that you have to work there. So research never ends, as you can see. But they're getting smaller and smaller. So they have done more chips on one wafer, and bring down the costs even more.
So
But
yeah.
yeah,
Now the chip that you show on the skin was also a 13 megahertz, 13.5 megahertz, or
yeah, that is
yeah,
13.56 megahertz. Yeah,
okay, good.
that is. Yeah.
And the chip has a coil inside also, right? And then you
The
have the
coil
booster
as the top metal layer
is
of
the
the
top
CMOS
man.
technology.
I see.
So
Nice.
it could be, that this chip is a bit more expensive because on the top metal layer, but I don't know it. It could be. So of course, just having one metal layer without any structure is way cheaper. But
No.
having a coil structure, it's again one lithography process that you have to add, maybe.
Yes, sure. So I think we have one last question. We are almost 1 hour, which is good. And this, from my point of view, was very fast. So it's a good conversation. So the question I have here is, if you don't have any technology constraint, what would your ideal vision for NFC charging look like in 10 years?
So this question was a tough one, I have to say, or is a tough one. I had the questions up front, of course, we agreed on these, and I really had to do a bit of research. So I was asking ChatGPT, so how would this look like, and can you create a figure for me? I completely
Nice.
failed. No, I failed. Oh God. No, ChatGPT actually failed. But the text that ChatGPT provided to me included one sentence that I liked a lot. And it was like, these hotspots would deliver just the right amount of energy needed for each device, reducing energy waste and extending battery life significantly. And this right amount of energy.
Exactly.
And reducing energy waste, that resonates with me.
Yeah. Reducing energy waste is really the key word that we need to do in all our electronic devices. I fully agree with you. And I think is the best the best word to actually close our discussion. I don't know if you want to add something else to this NFC rolled.
I would have loved to show you, answering your question and show you this figure created by ChatGPT, but it was like just not good enough. I might show it to you later when we meet offline. But in the end, I'm definitely devoted to make NFC charging also more sustainable and more efficient. And I'm happy that we're working on it, because digitalization is something that also can then improve our sustainable lifestyle. If you think of, you manage office buildings and empty offices or so, it's apparently one of 75% of the CO2 emissions are actually coming from these office buildings. And according to the European report, so if you could have an efficient use of this office building so that the offices are not empty all the time, like, or you just power them up and have, energy supply or whatever, like air conditioning, if people are inside there. So, this would really help us to create this green transition everyone is talking about. So that is why I'm a fan of the digital transition, but I also want to have, devices that can enable such a transition that are energy efficient and sustainable by themselves, also from an environmental point of view.
Yes, I thank you very much, Jasmin. I think it was an amazing discussion and conversation. I really like most of your videos. I think you have a tremendous prototypes, and I think this concludes our talk for today. Thank you.